I want to finish one little piece before we get into the review. So this is chapter 5.2. Last time we started it, and we stated this bunch of claim, and we verified it in one particular example. So today we're going to prove those claims, and then we're going to review. Okay? So let me set up what we claimed last time. Okay, so from last time, which we will prove today. Okay, so we have this linear programming problem that we solve with the, say, Simplex method, say, LP assistant. So if I put the initial form in this tabular form, I can probably denote it like this, where A is the matrix, and C now is a row vector, B is a column, Z0 is a number. Is that right? And then you perform some pivoting steps. Let's assume everything went through, and you have the final form where you could conclude the solution. So let's put this up. So like that. Then I have different numbers in my tableau. So the final one all carries the star. So that's the notation. All right. And then we want find the basic variables. Okay, so the basic variables in the final form, in canonical form, let's say this is with the index, so J1 to Jm. There will be m of them. So in your LP assistant, they will be listed on the left here. You can easily see them. All right. Okay, and then we form this matrix B by taking the corresponding columns of A column J1, and I put a vector here, and I take m of these vectors, and I put the last column here, so I have a square matrix. Is that right? Remember we did that in the example? And there is another notation. So I take out the same position from the C here. I call it CB. So this will be CJ1 to CJM. So C will have length m. With all that taken out, we made the following claim, which we'll prove today. We claim that A star equals B inverse A, and B star equals B inverse B. So these two are actually quite trivial, pretty easy. And the next two takes a little bit work to show. So C star, this vector here will be the original vector minus CB B inverse of A. And the Z is changed also, Z naught minus CB B inverse B. Okay, and then you see B inverse A is just A star, and B inverse B is just B star. All right, so we're going to prove this. Okay. Now, the book has a pretty lengthy proof, which I have decided not to follow. We do a different proof, borrowing one idea from maybe 220 in linear algebra, and the rest is just manipulation. Okay, hopefully shall be a shorter proof. So, okay, so I will using a lot of rearranging of indices. So we know that these are basic variables in those indices. So I'm going to rearrange. So a few steps I have to take. So first, rearrange indices so such that these will be the first m of my variables. Is that clear? That's what I'm going to do. Okay. So so such that J1 to Jm becomes the first variables, indices, okay? So which means I can write the following. So for this x now is rearranged. So everything that is rearranged, I will put a bar on the top. Is that okay? Without anything is the original one. With the bar is rearranged. With the star is in the final tableau. Is that okay? That's my notation. Okay. So if I rearrange, then I can rewrite my x, and I will have the basic variables, xb. Okay. I will put it, that will be the first m. And then I have the rest. I'll just call it xr. R is for the rest. It doesn't matter the ordering. Just put them there. Okay. And then I can rearrange the A matrix here in the same way. If I change two x's, what does it mean to the A matrix will be I just switch the columns. Is that right? So I will rearrange the A matrix so that the first column will correspond to the first variable x here in the rearranged one, right? So rearrange columns of A in the same way. Okay, so then the rearranged A, now, what would that be? Well, then I see that the first M column would exactly be this B. Is that right? That's why I took out the B like that. So A will consist of first this B matrix, and then whatever is remaining. So let's call it a D. That's whatever is remaining. It's a rectangular shape matrix. I'll put it there. Okay, and I do the same thing. Same thing for this C, this vector here. I rearrange it. So the rearranged one, I'll write it out. So what will I have? Well, exactly CB. Right? CB is taking these. Now I put these at the first M, and then I have the rest. I call it CR, which is a vector, a row vector. Yeah. Is that okay? That's just rearranging, calling them by different names. Okay. Let's see. If I am rearranged like this, and I did the carry out the same pivot steps, how would the final tableau look like? They will also be rearranged. The columns will be shifted. Is that right? And let's write this out. After pivot steps. Okay. So what do we have? Oh, we have this A matrix now, the final one, after with this rearranging. So you know that the first basic variable now will be the first variable, and the M basic variable will be M. What do you have on the left will be an identity matrix. Is that right? And then whatever is non-identity. This we have seen in, so I have an identity matrix, and then I have whatever is remaining part. Let's call it D star. I'll have that. Okay, so I is a identity matrix. Okay, and then what happened to the C that I rearrange? Then I know the first M are basic variables, and the objective function shall have 0 coefficients. Is that right? Because it has to be in canonical form. So what I will have here will be just 0, a row vector of length M or 0, and then with something that is non-zero, so I have CR star here. And then also know that all the coefficients here are non-negative, right? Okay? All right. So, okay, now let's interpret this pivot step. So all these pivot steps So what did we really do? We took the A bar and B and C bar, Z naught. After pivoting, I end up with A bar star, B star, and C bar star, and Z naught bar. So let's write in some detail. A bar, let's write out two matrices. A bar is just B and then having D next to it, right? And C bar is C, B, CR, and Z0. So meaning this, after the pivot, end up into the following. I have identity here, and I have this D. The right-hand side is unchanged. And for the C, I have 0, and I have C star bar. Just write that out. So we have all taken 220, right? Matrices, have we? Have we done this? Is it ever mentioned? Okay, so have we done this like you do the Gaussian elimination, you write an identity matrix at the side of it, and you pivot at the same time, and what you get there is the inverse. Is that right? And this is basically what you're doing. You pivot such that this B part becomes the identity. And then that one you put at the side will be the B inverse. Is that right? And all these pivoting steps, these are just linear transformations. Or you can say that this is equivalent by multiplying a matrix on the left-hand side of this equation will change this system into this one, which is equivalent. Have we heard about that? The permutation matrix, the changing of row, the multiply one line, add on the other, can be all represented by a matrix multiplied by this A. Is that okay? We borrow that idea, okay? All right, so this can be expressed, okay, interpreted, whatever, as let me write it down, multiplication of a matrix. Say, I call it M on the left. So what does it mean? This M is a square matrix of size M by M. So that means I multiply this by M on the left, I will get that. Okay, M multiply this will give me that. So this means A bar star equals M times A bar. If I write it in detail in terms of this expression, that means M multiplied by this matrix, first is B, second is D, will give me identity and D star. This means that. Okay, then this matrix multiplied by this matrix with two parts in it, I can multiply with the first to form the first part and multiply with the second to form the second part. And they must match I and D. Is that right? So this will give me the following. M multiplied by B must match the first part, which is the identity. And M multiplied by D will match the second part, D star. Is that right? I have this identity here. Now I need to find this permutation matrix M. What is it that I actually multiply? So with this relation, can we nail down the M? What multiplied by a matrix gives you identity? The inverse. Is that right? So M must be B inverse. Is that clear? So all these pivoting steps, in the end, what you do is actually multiply the system on the left by the inverse of B matrix. Is that clear? That's what you do. Okay, so now this actually we have proved the first part of the claim. Then we know that, okay, let's still stick to that. The shifted one gives me this, B multiplied by A shifted. And then you can shift the columns in A back and shift these columns in A back in the same way, and it will give you A star simply equals B inverse A. Okay? And that's this claim we're proving. And then you multiply the right-hand side, and then you get B star equals B inverse of B. Okay? So this one actually follows immediately. So we have the first part proved. Now we need to nail down those C and Z naught. Okay. Okay, well, let's look at the system after the pivoting, right over here. So what do I have? So in the final tableau, let's look at it. This one, what does it give me? It basically says I and D star multiplied by the unknown x, which now is index is mixed. So I will have the basic variables and the rest, right? They're ordered in this way, and that equals B star. So, okay, this is all look very fancy. I'm writing it like this, but you actually know once this is in canonical form, you can keep the basic variables on the left-hand side and put everything else on the right-hand side and express the basic variables in terms of the non-basic one, right? We do that all the time. So all these computations for me to get there. So I do this multiplication. I times xb simply is xb plus d times xr. That's something, and equals b star. So I can express the basic variable in terms of the other. Is that okay? Okay, so all this is to allow me to get my hands on this final line. Because you know what the pivot does to this final when we pivot down here. We express x, the basic variable, in terms of the other, and plug it into the objective function so that in the end the objective function will not depend on the basic variable. Is that right? That's this pivot. So now I already have this expression, so let's look at the objective function. Okay, so the objective function, what is it? Initially, it is CB CR times XB XR equals Z naught plus Z. Is that right? That's my objective function. If I write this out, I will have, it just looks fancy, CB XB. That is all the basic variables with their coefficients, and CR XR, the non-basic variables with their coefficients, equals Z0 plus Z. So that's my objective function. I want to rewrite it in terms of XR only. I don't want to write it in terms of XB, because in the final form, I must have all these 0. Is that right? So I have this, let's call it express I. Now I can express XB in terms of XR. All right? So I can plug it in. So plug in that computation, and then I can get rid of the basic variables on the left. Okay? So if I do that, I have the following. CB, XB is B star minus D star XR, that's that, plus CR XR equals Z naught plus Z. Now you see, in this objective function, the only variables that appear are the non-basic ones. Is that right? That's what we do to it, right? Okay, so let me rearrange terms. So let me distribute first. I have CB B star minus CB D star XR. I just distribute and I copy the rest. Okay? And then I see that this term is just a number. Is that right? CB is the coefficients here, and the B star is the constant column here. That's just a number. So I would move it to the right-hand side. Is that clear? And then I have the XR as a common factor on the left, and I collect it. So what I will have will be CR minus CB D star XR equals C naught minus C B B star. I'll move it over here plus C. It's just moving terms around. It's not really. Okay, so I express the objective function now in terms of the non-basic variables, and then I found out this constant term on the right takes this form. Isn't this exactly the z after the pivot, right? That's what we will have over here in that. Okay, so looking at this expression, isn't it exactly this one here? This guy here is just B star, and this guy here is just A star, right? So we have that one already. Okay, now we need to verify the final one, that is the C there. So, which means this left-hand side, in the end, it's this form in the left-hand side, and we want to show that this C bar star is C star is expressed by that. Okay, so let's take a look at this. Let's call this left-hand side. So what do we have left-hand side? I know this is in terms of the non-basic variable, so I can think that I have a 0 vector. That is actually what happens, right? Multiplied by the basic variable plus CR minus CB D star of the non-basic one. Is that right? I can think of it like that. And so I can merge these two vectors and merge these two and write it as a product of two vectors. So I'll have 0. That's this 0 vector. And then I have CR minus CB D star multiplied by XB over XR, which is just X bar. Okay. So let me call. So you know this would be my C star after pivoting, but index rearranged, right? And this is just X, right? Rearranged. So let's copy. This will be C bar star X bar. So I know in the end, in my table, I will have this expression, which is this expression. So I need to show that in the final tableau, this C bar here, star, shall fit the formula that I claim it has to be. So it shall be that expression, but with all shifted index. So it will have be C bar with shifted index minus CB, B inverse, and A shifted. If I can prove this, then I'm done. I can shift the columns back. I will get my claim. Is that right? So now it remains to show this identity. Okay, let's check. Okay, I'll start from the right-hand side, and then I will show that it equals this, the left-hand side. Okay, So let's look at the right-hand side. C bar minus CB, B inverse A bar, what does that equal to? Well, what's the C bar? C bar, let's write it out, is CB and CR have two vectors, minus CB, B inverse. And what is this A bar? Well, A bar, I can write it as B and D, right? I rearranged it. Okay, let's do a little computation. So I have C, B, CR minus. So I can distribute this inside and multiply each, right, and form the matrix afterwards. So I have CB, B inverse B. That gives me a square matrix. And then this times that, CB, B inverse D. Okay, let's look at what we have. I have this B inverse multiplied by B, which will give me identity. Is that right? And identity multiplied by any vector give you this vector. It's like 1, so this, I can cross it out. It doesn't do anything here. Is that right? And I also know that B inverse times D, and isn't this what we call it, D star? Is that right? That's what we had here, D star. D star is B inverse times D, right? Okay. And then what I have is a vector, subtract another vector. And the first vector, the first m element, equals to this first m element of the second vector. After subtracting, you will get all zeros. You just subtract the same position, right? So I will have 0 to 0, length m, as the first part, and the second part will be this minus that. So let me put comma. CR minus CB D star. Is that right? Isn't that exactly what we claimed it has to be? So that's C bar star. All right. Now the proof, okay, that is just a proof. So we proved this part also. Okay. So I want to block these relations here. Look at, let me remove this mess, A star and B star. So you see clearly the original form of it. So this expression now becomes very, very useful when we want to do sensitivity analysis, isn't it? Look, that will be the optimal value in the final tableau, that place. And now with this expression, you see clearly how it depends on the Z naught as the initial part, and the B matrix, that is taken from this A, and the C, that's taken from this C, and this B, that is the right-hand side, right? And you see if I change a little bit of this CB, for example, and I see immediately how this is going to affect my final answer. And if I make a change in the B, and you see how it goes into change the final answer, okay? With this, it makes the sensitivity analysis much easier and much clearer, and we can do all different of analysis. How changing the constant column will affect you, how change the objective function will affect you, and how if I add a new constraint, I add a new variable, how does that affect me, all right? So that will come after the second exam. So any questions? Is that okay? So after the exam, we'll come back to this and do more sensitivity analysis. All right, now let's do a review. Let me remove this. I got a couple of emails from some students asking specific problems to go through, we can do that, or you have other wishes I can take at the spot also. Oh, come on. All right, so let me put up, before I forget, extra office hours. So if you shall need help, I'll give some extra office hours tomorrow, one in the morning, one in the afternoon. So I think that's what I put on the board in the other class. Is that okay? And I do have to leave shortly after that. I have to pick up my kids. All right. So that's that. And the exam will have 7 problems, okay? In the guide, it says 6 to 7. So it will actually take more or less a very similar format as the first exam. 7 open-ended problems, total 50 points, and I do not allow you to bring any books, any notes, anything. You don't even need a calculator. It won't help you. Is that okay? Just everyone's treated the same, okay? I think the main concern you are having would be like, or if you're uncertain about the part with proofs. Usually we're not so comfortable with all these. We're not so well trained with proof. Let's like go through some chapters in the book where it's a bit unclear of what kind of a proof I can put up. Just so you can be more focused and more targeted when you review, all right? So I think one chapter that's a bit unclear, several of them I'll mention. So chapter 3.8. That is something we covered before the first exam, but it was not in the first exam. It was the convergence proof for the simplex algorithm. Do we remember proving there? It was pretty lengthy. It took more than a class, right? That proof is really long. You know, there's no way I can ask you to cough it up in 10 minutes and put it on the paper. So in that chapter, there are many like theorem, lemma, whatever, many statements claiming, okay, this we proved, and this result is like this and like that. And also, if you look at the homework problems of that section, there are many like statements. Can you tell me if the statement is true or false? Okay, so yeah, you have to think like me, right? If you were to make the exam, what problems can you put in, right? Yeah, so I would say that you have to review all the theorems there. Review the theorems, or whatever, lemmas. And you have to be very clear of the results, all right? So the statements, you have to be very clear, the statements of these and what they actually mean and how you can apply it to check some situations if it's true or false and what you have to do, okay? So, is that okay? I think I'm saying too much. I try very hard to pull your average down, but now I'm doing the other way. Okay, that's that. And then 3.9. Convexity. Did I spell it right? I'm confused. Now, this is a chapter that I feel a little bit uncomfortable. I might have said it in the class that personally I regard this as the highlight of the course. That is the core idea, the most important theoretical result. And the book covers it in 2 pages with very little stuff, right? And okay, I'm a mathematician. I cannot resist presenting this beauty to you, and we covered it in more than a class and a half. We went through a rigorous definition from convexity, and the step by step we went through definition of convex set, what is a vertex, what is an edge, and relate all that back to linear programming. Remember? And now in the review I did say you have to know very clear these definitions of these concepts, right? What is a convex set? Do we all know? What does it mean a set is convex? In my lecture, I give a formal definition. The book doesn't have a definition. You just say it's like this and that. Okay. You have to know that, and then we defined what is a vertex, what is a corner, right? And we defined what is an edge. So you have to be clear in your head what are all these definitions, okay? And we also went through some examples, some simple proofs. Give you a set. Can you show it's convex? I give you a corner. Can you show it's a corner? It's a vertex. Can you show some simple proofs like we did when we covered that chapter?
So
yeah.
Do we need to know the proof for the disk, like the x squared plus y squared thing?
That everywhere on the boundary is a vertex?
Yeah, do we need to know that proof?
No.
Okay.
That would be nice if you can prove it. Yeah. It's not hard, but it's a bit different from the proof that I gave in the class. Yeah, because the boundaries are curved. What we had is boundary have edges, and this one doesn't have any edge, but it has vertex everywhere. So it's a nonlinear problem, and we restrict our discussion to linear ones. Okay? Yeah. Yeah. So it's okay. So you might want to watch the video of that if you feel uncomfortable with it, and check. And yeah, you have to copy down the notes. That's what we do there. Okay. That's that. And then, okay, I want to say a few things of these two chapters, 4.3, 4.1. That one is the introduction to the dual problem. The other is more interpretations of the dual in the real life situation. So imagine you were me. What question can you come up of this in the exam? It's nice to understand the connection of the dual with the original problem in the real life setting. Like, it's like you're playing a game with a opponent, right? If you can reach an agreement, so the game has a solution, and then the problem viewed from my point and from the other one's point, we are dual problems of each other, right? So, so how about I say, read it as a storybook, just softly. Okay, it's nice to understand, to have understanding of what they are, but I can't give you a problem and ask you to write a story about it. Okay, it would be a nightmare to grade. You agree? I can't grade something like that. All right, so that should kind of make it easy. And 4.2, well, that's set up the dual that you should be able to do. That's trivial. And then another really big one is the duality theorem, 4.4. So that's the other highlight of this course. So duality and the convexity. Those are the two core ideas, okay? Very important. Okay, so in the duality theorem chapter, we started with the theorem. We have corollary, and another theorem, and some corollary, blah, blah, blah. And some of the proofs are not very long, and then we have some homework problems. So I would say you might want to be careful with all the proofs that we went through in that part. Make sure you understand. Is that okay? I can take part of it out and ask you to prove it to me. So there'll be proof problem coming from that, either similar to what we covered in the class or in the homework. And I will not ask you to prove something that is new, that you have to come up with a proof. Is that clear? Okay. I'm leaking too much information out. And now what is important also is this application, right? So let me put star. So be very careful with this chapter here, okay? Be sure you know all the results. Be sure you know how to apply it and what problems you will be facing as applications and how to apply the duality theorem, okay? They're both required. You need to be able to prove and you need to be able to apply that result to problems, okay? And then 4.5, there and the complementary slackness theorem. Well, there is not really a proof there, right? It's all proved in the duality theorem. We just took that part out and make observation and stated the theorem, and that's all. So here I would focus on applications, meaning solving problems using that theorem, as you have done, or maybe you haven't, for this homework that's due today. All right? Okay, so you need to be able to know how to apply. Okay. And then 5.1, that is something we covered last week. So that is an introduction to sensitivity analysis. Sensitivity analysis. So it's an introduction. We looked at it for very simple problems, for simple LP problems, meaning problems with two variables that allows you to sketch the feasible region that you can do a complete analysis. Is that right? So here one can actually write out a complete analysis because the problem is so small, okay? So what we do is we use graphs, right? We sketch the feasible region and then the contour line of the objective function, and we move it and see where's the optimal. You can just visually see it, and then you can write out, like you did in the homework. There are two problems in that direction. Is that clear? So one must be able to do that. And then we didn't do anything else on sensitivity analysis. That will come in the final. You'll be tested on that. Yeah. Does this help? Is it clearer what to expect? We feel more comfortable? All right. So it will be in class. It will be 75 minutes, 7 problems. You have about 10 minutes on each problem. Some problems are simple. Maybe in 2-3 minutes you can be done. Some might take you a bit longer. Okay, there are a couple I expect to take some time from you. You have to think. Okay. All right, so what should we do for the rest? Any special requests?
3.8.4.
Hmm?
3.8.4. Practice.
3.8.4. That's a true and false. The answer is true, and you don't need to give any reasons for that.
Okay.
Yeah, so okay, so you are thinking of here true and false, right? So these type of true and false will not be as tricky as those in the homework set that you actually need to do a lot of analysis to figure it out. It will be more like very similar to the statement of the result, but I might put some false claims that you should see through. All right? No proof is really needed to get that. Is that okay? Yeah. Let's see. Do we feel comfortable of these two sections? That's what I was thinking, because we just covered it last week. It's kind of still pretty fresh, not cooked yet.
Do we need to know the shadow price, what the meaning of it, and how to use?
Not for this exam. No. Yeah. If I give you shadow price, and I have to give you the table from the LP assistant that you can find the solution of the dual. Yeah. Yeah. Okay, so any problem you wish me to go through? I have a request of going through 4.5, problem 3, part E. Shall we do that? It's to use the complementary slackness theorem. Would it be okay if I do that? Or, because I think that might be useful. The procedure is pretty long, and you shall not forget all the steps. You have to go through all of it to reach the final conclusion. Otherwise, it's not correct. All right, so let's do that. I think in class we just had only 2 examples that wasn't very much covered. So 4.5, problem 3E. So let me copy the problem out. 4.5, 3E. Okay, so it asks you to prove or disapprove. So basically you want to check if a point 0, 3, 12 is an optimal solution for the following. Let me just write out minimum. Minimizing 2y1 minus 5y2 minus 3y3 subject to. I have 3 constraints. Negative 3 y1, negative 6 y2, 2 y3, 6 y1 plus 3 y2. Okay, they're all positive, so I'm not write that. And the problem states clearly that you need to use the complementary slackness theorem. So you have to use that, all right? Not doing with any other. You might be able to prove it with other things or check it, but you have to show me you know that part. It's to check your knowledge on that theorem. It's okay? So follow the instruction in the text. Always do it. Okay, so here you actually have to take quite a few steps. So let's go through that so you know for sure you don't miss any of the steps. Okay? So how about I call this y star, so it's easier for me to refer it. So step 1, what do you need to do? I need to check if y star is feasible. If it is not, then you stop right there. It has to pass this check. And if it is feasible, and then you need to find the slack. Okay? And let's call the slack W. Then it's easier to refer to. Okay, so if you do that, you put in these number, and you will find out that, can you fill in this detail? You know how to check it? Putting this y1, y2, y3 as this number, compute to the left-hand side, and see if the relation holds, and find how much is the slack. All right? So you will find the slack is the following: 0, 1, 0. So the first and the third constraints are satisfied with equal sign. The middle one is strictly bigger than sign. It's okay? That part you do. And then second part, you must form the dual. Okay, so you see it takes some work. Okay, let's form the dual. So I need to maximize. So now I have xy, 6, x1, 20, x2, 15, x3, subject to. I'll have 3 constraints, and they're all positive. I'm not writing the positive thing, but you should. -3, x1, x2. I need to write out the dual carefully because I need these equations. Maximize less than 2, -6, x1 plus 3, 7, less than -5, and then the last is 2, 1, -3, 2, 1, -3, less than -3. Okay, and they're all positive. You have to put that out. Okay, that's the part. You have to form the dual. And now we would use the theorem. So, okay, so we need to verify if y star is optimal, right? Or we need to check if it's optimal or not. So let's assume it's optimal. And if we don't reach any contradiction, then it remains optimal. If along the way something goes wrong, then it's not. Is that clear? So here goes the argument. Assume y star is optimal. Okay? So the first problem has an optimal solution, so the dual will have an optimal solution as well. Is that right? And then we denote that by x star be an optimal solution for the dual. Okay? Then okay, and then let's denote also the slack is v. So v1, v2, v3. Okay, and then we apply the theorem. So, okay, so here you actually applied the duality theorem, didn't you? You assume that this is optimal. By duality theorem, the dual problem will have an optimal solution as well. Otherwise, you cannot claim that this is the optimal, right? So you use that. Okay, and now we use the complementary slackness theorem. If these two are optimal, the theorem says that x star dot the slack for y must be 0, and y star dot the slack for x must be 0. That's basically what that theorem says, right? Okay, so what can we conclude from here? Then you go to the W here and you find out where it is non-zero. Wherever it is non-zero, the corresponding x must be 0, otherwise you won't get 0. Is that right? So this tells you x star of 2 must be 0, because the second position of W is positive. Is okay? And then the same thing for this part. I know my y star is given here. And based on that, I can find out which element of the slack v has to be 0. Okay? Wherever y star is non-zero, and the v must be 0. So v2 must be 0, and v3 must be 0. Is that right? So what does it mean? That means the second and the third constraints are satisfied with equal sign at this optimal solution. Is that clear? Now we put it together, and put together and we try to find out. Okay, so we already know x2 star is 0, so what do we need to do? We need to still find two others, x1 and x3. These two we still don't know, is that right? So what I did in the class was we went back to this constraint and we look at it. I know x2 is 0, so this will not enter in my equation. And then I also know I need the second and the third constraint. These two will be taken. So the first one actually will not be taken to form this equation. So I see I have two unknowns, and then I change the inequality into equal sign. I solve for it. Is that clear? So I have the following. Negative 6 x1 star plus 7 x3 star. Now I have equal, okay? Why do I have equal? Because the slack is 0, okay? So the last one, 2 x1 star minus 3 x3 star equals negative 3. Okay, then I can solve for this. Are we okay solving this? Two equations, linear equations. You can use substitution or elimination, whatever your favorite method. I'll let you solve that. 9, 7. You can plug them in and see if that's correct. Okay, which means I have a candidate for the optimal solution, 9, 0, 7. Am I done? Do I still have to do something? What I haven't done. Be very careful, don't miss that step. So far everything went through, but I still have one more thing to verify. We have to verify this is feasible, is that right? Which we didn't do. So we need to check if x star is feasible. Meaning these three constraints, the dual problem, is that right? So do I need to check the second and the third constraint? Do I need to? I don't, because I know they will be satisfied with the equal sign. That's how I found these two x's. Is that right? You only need to verify the first constraint, the one that's not being used when you form this equation. Okay? So only for the first constraint I need to check. Okay, let's check. So x1 is 9, so I have negative 3 times 9 plus x2 is 0 plus 4 times x3 is 7. What do I get? 27, 28 is 1. I need it to be less than 2. Is that okay? Yes. So what can you conclude? My assumption is correct, right? I assumed it, and then everything went through by the complementary slackness theorem. That will be the optimal. Don't forget to conclude, okay? Then you have to say, we conclude y star is optimal. Then you're done. Is that clear? The steps you have to go through? Now, if along the way something goes wrong, then you don't have to complete everything. Is that right? You have to complete everything. If this answer is yes, then you have to go through all of it. Let's say in the computation, when you are trying to find x, let's say just for example, if I find this is negative 9, the other is 7, do I even need to go and verify it? No, then you already know that is not going to be feasible, right? So it has to completely go through. Is that okay? All right. Hope that helps. So anything else you wish me to go through? Any?
Are there situations that the number of equations is less than the unknown?
It should not be. They might be more, but they should give you the same answer. One will be redundant. If you have a redundant system, that could happen. Yeah. Now we still have 9 minutes. Anything else you want me to cover? Okay, let me make a remark. You go and read it. I know you're just turning in the homework today, and what's on the homework will be on the exam, which made me a little bit uncomfortable. So so homework 9 answer will be posted after midnight tonight. Is that okay? It will be available. I will set it up so Canvas can delay my post, and it will turn on exactly after that. Okay, and you should go and read it, and I recommend you to read it. Okay, it's important because these are covered in the exam. Okay, so you have plenty of time to review it, and in particular, the problem 5.1, problem 7, Patsy. I want you to go and read it. Is that okay? Just read that answer sheet. So that is a slightly more complicated situation than the one we did in class, and we did not exactly cover the same thing, but if you understand the basic concepts, the guideline very well, you would be able to solve it. But I want you to read the answer as well, so you know clearly what to do. Is that okay? Mm-hmm. All right. Now, that means, because every homework, there are some students that say, oh, I tried to submit 5 minutes before, and then I got stuck. I didn't manage to submit. I got the email the day after. May I still submit? Now, the answer will be posted. Now, this, I'm going to be mean. No late homework. I will not. I will not. No late homework will be accepted for this one. Is that okay? Fair enough? Because the answer will be there immediately after midnight. Okay, so make sure you submit. Try to submit at least half an hour before the deadline to allow some time if you get stuck or something. All right? All right, so if you have questions, there's the office hour. You can come and get help. Otherwise, happy studying and good luck.